Hey everyone, it's Justin again. In this lesson, you're going to learn all about the incenter of a triangle. More specifically, you'll learn about what the angle bisectors have to do with the incenter. The notes I show you today will have lots of different colors in them, so if it helps you to use different colors when taking notes, I recommend having 4 different colors ready to use. Before we get started, pause the video now and collect some different colored writing utensils if you want them. By the end of this lesson, you will be able to apply the properties of the incenter to compare lengths and solve for unknowns in a triangle. First, we'll explore how to find the incenter through an activity in your notes template. Then, we'll complete one multi-part example problem. This is the first page of your notes template for this lesson. It has a link to follow that will provide you with a visual representation of the incenter. This visual is interactive and allows you to move the vertices of the triangle to see how the incenter changes. There's a graphic organizer with blanks for you to fill in after you explore the visual representation. You've already completed an activity similar to this in the previous lesson, so you may choose to approach this in a similar way or alter your approach, now that you know what's expected. So pause the video, follow the link, and figure out how the incenter is defined. Let's check your work with the key before completing an example problem. Go ahead and check your answers now. If you had something wrong, it's really important that you go back to the link for the visual again and explore the idea that you were missing. Pause the video so you can do this now. Let's move this over to the side so I can show you a few things on this triangle. Here are our 3 angle bisectors for this triangle. We can see that they meet at a point, and this point is the incenter. The incenter is the same distance from all 3 sides of the triangle. Remember that lesson in the previous unit about the perpendicular distance being the shortest distance to get to a line or segment? That's exactly what happened here. When connecting the incenter to each side, I had to use a perpendicular segment. We know these distances are all the same because the largest circle we can fit inside the triangle actually has the incenter as its center and has all of these distances as its radius. So there we have it. This is the incenter. It's the same distance from each side and is formed by the angle bisectors. If you need any more time with this, go ahead and pause the video now before we move on to our example problem. This example problem says, given that point A is the incenter of triangle BCD, complete each statement below with an inequality, an equal sign, or a numerical value. So, how is the incenter found? What relationship exists between the incenter and the distance to each side of the triangle? Try doing some labeling on your picture before we worry about filling in the blanks to answer this problem. Mark as many segments and angles as congruent as you can. Pause the video and do this now. We know that the distances from the incenter to each side of the triangle are congruent because they're perpendicular to their sides. So we can mark those. Since the incenter is where all the angle bisectors meet, we know that connecting point A to all the triangle's vertices will bisect each angle, like this. Now that we have all of our congruences marked, let's check out the parts of this problem. These 3 answers will involve inequalities or an equal sign, and these final 2 sections will require a numerical answer. Think of this as a 2-part problem so it doesn't seem so big. Try to get through the first section, and then see what you can come up with for the second section. Pause the video now, and try this problem out on your own. Let's see how it went. Our first comparison is between angles GDA and FDA. We already knew these were congruent because we're working with the incenter, so we can write that the angle measures are equal. Next is AF and EA. These were marked congruent earlier. If you're forgetting why, remember that if we put a circle in the triangle that touches all of its sides, these would match because they'd be the radius of that circle. So we can say their lengths are equal. Moving on to AB and EB, we can see that this right triangle will allow us to make comparisons between the sides. Since AB is the hypotenuse of that triangle, it has to be longer than EB. Woo! We made it through the first group of questions. The last two answers we give will need to be the actual numbers since there are equal signs already in them. Let's find the length of AG. We marked these as congruent earlier, so since AE is 6 units, AG will also be 6 units. Finally, we have to find the length of AC. A right triangle is going to be helpful here again because this will allow us to use the Pythagorean theorem to solve for the missing side. We can also use the fact that these two sides are the same length to get another leg of our right triangle. Now we just need to solve for the hypotenuse or the length of AC. If you didn't get this far on your own earlier, pause the video now and see if you can find the answer to this. Substituting 6 and 10 into the Pythagorean theorem and solving for the hypotenuse of this triangle gives us that 2 times the square root of 34 is the length of AC. Great job with this. Now you can apply the properties of a triangle's incenter to compare and find lengths, and don't forget that the Pythagorean theorem may be useful when there's a right triangle involved. We're going to learn about some other special segments in triangles in the following lesson, so don't forget that it's the angle bisectors that form the incenter. See you next time!